Hello everyone, and welcome back to the series on financial mathematics. Today we're going to be continuing our exploration of special annuity structures and introduce a special type known as a geometrically increasing and potentially geometrically decreasing annuity structure. So just a quick outline of some of the things we discussed so far. So obviously we have our traditional classic fixed level payment annuity immediate, which is just fixed payments of size m starting at t is equal to 1 all the way down to t is equal to m. Using our typical present value sequence, that's just nu plus nu squared plus nu to the power of n to get our present value, which we know is just the reciprocal of our effective interest rate times 1 minus nu to the power of n. And obviously if those payments are of size m, not necessarily 1, then just multiply that present value formula by m, and that gives us the typical structure that we use for loans under amortization. Then we have the arithmetically increasing strategy, where we increase by some fixed value, let's call it L, each payment. So we go from 5 to 10 to 15 to 20 to 25 to 30, all the way down to the last payment. And that gives us what we call arithmetically increasing, because that increasing value is fixed every single time. And obviously via the typical present value sequence, that's just the 1 discount to the first, 2 discounts of the second, all the way down to n discounts of the last, and that gives us that particular sequence. In the last discussion, we were able to actually derive a very nice representation for this, and we denoted that present value by IA for arithmetically increase in annuity immediate with m payments under I, where the first payment is of size m, and it increases by L on each iteration, and that's just going to be equal to m times the typical annuity immediate present value plus the amount we increase divided by I, multiplied by, again, that present value of an annuity immediate, minus n nu to the power of m. And we're able to get this very beautiful and simplistic representation. So before we get into the geometric increasing thing, I just want to look at a couple of variations of this formula that are also common in practice. So the first variation that I want to look at is when m is equal to 1 and L is equal to 1. This is often called the unit or basic arithmetic increasing sequence. We start at 1, then we go to 2, 3, 4, 5, all the way down to m. So it's in some sense our base case. So obviously our present value, which we can just denote as IA11, right? So we can call it IA11, and I, that's just going to be equal to what? So that's just going to be equal to A and I from the formula, plus 1 over I times A and I, times minus n nu m. And obviously we might be able to simplify that a little bit because keep in mind that has a 1 over I in it, that has a 1 over I in it as well. And there can be some algebraic manipulations that can make that a little bit more nicer to deal with. But a more different style variation of this is where, for example, m is equal to, let's call it, say, little n. And where L is equal to minus 1. So instead of it increasing by each iteration, it actually decreases by a particular iteration. So if we look at a particular timeline, what would that actually look like? So we have 0, 1, 2, all the way down to m minus 1 and m. So we start off with 0 and then m, then it decreases by 1, decreases by 2 if we sort of go to 3. And then it goes all the way down to what? So then it's going to be n minus, want to take a guess of what this is going to be? Well, it's actually just going to reduce to 2, and then we're going to have a payment of size 1. So what we have here is an arithmetically decreasing annuity because our L is negative. But do we have to start off with a payment of size equal to the number of payments we have? Of course not. And do we have to decrease this by 1 each iteration? Of course not. So if you want the generalized arithmetically decreasing annuity immediate structure, where we have, for example, 1, 2, 3, all the way down to, let's go to m minus 1 and m, where we start off with m again, but now we're going to go down. So we're going to do m minus L, m minus 2L, all the way down to m minus n minus 2L, down to m minus 1L, you should realize that the present value structure is practically the same thing from the timeline perspective, except with a minus sign in front of those L's. And that observation actually is very, very important. So the present value will just be equal to an IANI with an M minus L structure, and some people will even denote this with a new notation, because why not, using DA. So instead of increasing, it's decreasing arithmetically. NI starting off with M, decreasing by L each time, and the closed form for that present value obviously would be equal to MANI minus L over I. That's the only place in the formula where L is present. And then we're going to have ANI minus NUM, and that would be the present value of an arithmetically decreasing annuity immediate with first payment M that decreases by L each time. Right, so those are the structures that we have up to this point. Now let's introduce our next very important annuity structure. So this structure is going to be referred to as a geometric annuity, and this is going to how the payment structure is going to be set up as. So we're again going to be starting off with 0, so this is going to be a geometric annuity immediate, and we're going to be aiming for the present value of this. Our first payment is again going to be M, and then M is going to increase by a certain percentage, and we're going to represent that percentage by lowercase letter g. So right off the bat, you should be able to see that this is going to be very similar to how interest compounds monthly or daily or weekly for a typical savings account. So you're like, okay, maybe I can structure a loan to have payments that increase in parallel to how my savings accounts are increasing. And then in some sense, I can start to price match those particular financial products. So if it increases by G%, again, obviously G has to be greater than 0, then that means at time t is equal to 3, this is going to be M times 1 plus G squared. Technically at 1, it's going to be 1 plus G to the power of 0. That's obviously to the power of 1. And if we continue all the way down to N minus 1, what power would that be? Take a moment, pause this video if you need to think about it. But notice that we have 1 subtract 1, 2 subtract 1, 3 subtract 1, and then m minus 1 subtract 1. What would that be? That obviously would be m minus 2. And the last payment will have a value of m times 1 plus g to the n minus 3. Right? So here the payments are increasing geometrically. So in comparison to that of our arithmetic increasing value, so if we look at our payment values of M at time t is equal to k, where k is on the horizontal axis, this line represents our arithmetically increasing values, assuming that we start, for example, at value M, and then over here we are going to have this particular structure. So this is going to be our geometrically increasing structure, right? And obviously this should reminisce from our discussion, for example, with simple interest rates and compounding interest rates and force of interest rates and so on. So now we're just talking about annuities from the same exact perspective. So if we have this particular sequence where we have a first value of M and it's increasing by G%, then what is that present value going to be equal to? So notation-wise, we're going to be representing this as GA for the present value of a geometrically increasing annuity immediate with M payments under I, where our first payment is of size M, and we're going to be increasing with respect to G percentage each iteration, right? So our goal is to have a nice little formula for this particular object. We have our timeline, so you should be able to at least write this in expanded form. So if you are used to this type of thing, maybe pause the video and see if you can figure this one out on your own. So if you don't, let's just follow along to see what that's going to be. So our first payment is of size M. That's obviously going to be discounted once. And then our next payment is M, 1 plus G. That's going to be discounted twice. And then we're going to have 1 1 plus G to the power of 2. That's going to be discounted 3 times, all the way down to our last payment of M times 1 plus G to the M minus 1, which is going to be discounted n times. So notice that every single one of these expressions has M in it. So I can obviously factor that out of our expression, and I can write this as M times, And then what are we going to have? Well, we're going to have nu times 1 plus g v squared, 1 plus g nu cubed, all the way down to 1 plus g m minus 1 nu m, which is just going to be equal to, again, a geometrically increasing annuity immediate with m payments under I, with starting payment 1 that is increasing by g. Some people will call this just a unit annuity. Some people will even take this to be equal to a new notation as well. They'll just abbreviate it as GAN subscript I, also subscript G as well. So this notation is just a unit geometric annuity immediate. Right? A unit geometric annuity immediate, or geometrically increasing annuity immediate, right? So our goal is to find this. So if we can find this present value of a unit geometric annuity immediate, then we can just multiply that by m, and that gives us our general present value for our general geometric increase in annuity immediate. So let's find GA first, and then we're just going to multiply it by m. So what do we get? So we have GANIG is going to be equal to 1 plus g to the power of 0 times nu, plus 1 plus g to the power of 1 times nu squared, all the way down to 1 plus g to the power of m minus 1, nu to the power of m. So we can easily write this in summation notation, or just have a slight shift to deal with, but that's just going to be equal to the sum from k is equal to 1 to n. We could do that from 1 plus g to the power of what? So notice 1 plus g starts at 0, so if we put that as k, since we start at 1, we have to subtract by 1 to start at 0, and then obviously our nu's are going to match our indices, since it goes from 1 up to n, and 0 goes from, k is equal to 1 ranges from 0 to n minus 1 under k minus 1. So everything in this particular notation matches, or you could do this equivalently as the sum from k is equal to 0 to n minus 1 also, and just focus on the powers of 1 plus g. Here they're going to match just with g, and then nu is going to be k plus 1. That is also perfectly fine. So you can get the same exact answer in either variation. It doesn't really matter. Whatever you're most comfortable with, just go with that. But I'm going to go with this particular variation just because. Nothing special. So we're going to have GANIG will be equal to the sum from k is equal to 1 to n. Now notice here, if I want 1 plus g to be raised to the power of k, I'm missing one of the 1 plus g's, am I not? So actually I can write this as 1 plus g to the k all over 1 plus g to the 1. That's going to give us 1 plus g to the k minus 1, and once I simplify that, and that's going to be times 1 times nu to the power of k. This 1 over 1 plus g can be actually factored out over that particular object, and that's going to give us a nice expression to work with. So we have 1 over 1 plus g, and you'll realize why this is nice momentarily. So we're going to have the sum from k is equal to 1 to n of 1 plus g to the power of k times nu to the power of k. Notice that everything has a k power, so if you remember some properties about exponents, exponents distribute nicely over multiplication, so that's just ak bk. So I can actually factor out that exponent outside of this bracket, and I can write that as just 1 over 1 plus g times the sum from k is equal to 1 to n of 1 plus g times nu to the power of k. This is just a number, and this ranges from 1 to n with some power of k. So now we can use our typical summation tricks on this particular object. So what is that going to be? You might want to pause this video and try this on your own if you're confident, but that's going to be equal to the following. So we're going to have 1 plus g nu, that's our number, minus 1 plus g nu to the power of n plus 1, all over 1 minus 1 plus g nu. Right? Number minus number to the power of n plus 1 over 1 minus number. That's our typical sequence for our finite arithmetic series. Right? So there's lots of things going on here, so let's try and clean this up the best we can. Firstly, notice there's a 1 plus g nu here, and there's m plus 1 1 plus g news there, so I can factor 1 out. And also, I'm just going to factor this object out of the bottom here, and I'm just going to write it as 1 over 1 plus g times 1 plus g times nu all over 1 plus g to the power of nu there. And then I'm going to have your 1 minus, let's actually put this in brackets. You might be able to see something very familiar here. 1 plus g to the power of nu to the power of n, right? So we have this particular object. And I'm going to leave this here, and I'm just going to introduce a couple notations here. So again, this is GA, NIG, and we'll clean this up momentarily. So this 1 plus g nu, you obviously see it everywhere, so maybe there's just something special about it. So if we look at 1 plus g nu, nu is just 1 over alpha, so that's just 1 plus g times 1 over alpha. And alpha is just 1 plus I, so this is actually just 1 plus g all over 1 plus I. So if you realize, since this is, if g is equal to 0, then this is just equal to our discount factor nu, right? But this nu depends on g, so this actually has a name. It's called the adjusted effective discount. Actually, let's not call it effective. Let's call it the adjusted periodic discount factor, right? So it's almost like the typical 1 over 1 plus I is equal to nu, but it takes into consideration a geometric increase. So it's trying to combine both how I increases and g increases simultaneously. So we have our adjusted periodic discount factor that's adjusted with respect to our geometric discount rate, g, right? And that's what 1 plus g times v is. So that's cool. So let's go back to our relationship for GA and IG. So that's going to be the geometric increase in n, and then I, and then g will be equal to what? So we have 1 over 1 plus g times nu g over 1 minus nu g, and then we have 1 minus nu g to the power of n. And you're like, this looks awfully familiar. And you would be right. So what we have here, if we define 1 plus I all over 1 plus g, if we define this to be equal to alpha g, which obviously is the reciprocal of our nu g object that we have, this would have to be equal to 1 plus some effective interest rate that also depends on our g, right? So we can define that object as well. So we're just defining 3 new interest rates that sort of combine both I and g into the same exact realm. And one lovely exercise that I leave for you is that nu g all over 1 minus nu g, if it was just nu, do you remember what nu over 1 minus nu was? You should remember that's just 1 over I. And you should be able to verify that this is actually 1 over I g, right? So you're like, oh, okay. Now I see some patterns. So let's go back to our geometric increase in annuity immediate formula, and we're going to have the following. So we're going to have GA with M payments, effective interest rate I, geometric increase rate g, is going to be equal to 1 over 1 plus g multiplied by 1 over I g times 1 minus nu g to the power of m. And what exactly is this? So keep in mind, nu g depends on ig, and n depends on n. So that is just precisely an annuity immediate under a different interest rate ig. So we can write the following very interesting result. So that's going to be equal to 1 over 1 plus g multiplied by a n ig. Right? So it's an annuity immediate with M payments under effective interest rate IG, right? Where IG is equal to 1 plus I all over 1 plus g minus 1. I recommend you try and verify that result on your own. Okay, so we have this very beautiful identity for calculating the value of a unit geometric annuity rate, and then we can multiply that by m to get our general structure, right? So let's actually just summarize this very nicely. So therefore what? So that means GA NI MG will be equal to m all over 1 plus g times a n IG. Okay, so that is our very simple formula for our present value of a geometrically increasing annuity immediate with m payments under I, with first payment m that increases by a factor of g. Now, let's go back to the context of loans and see if this performs better for the consumer or business compared to that of the arithmetic increasing and also the fixed payment annuity increasing structure. Alright, so we're going to be taking the same exact example as we did in our arithmetically increasing annuity discussion, where we take out a loan of 82 grand under an APR of 4.1% for 6 years. Everyone should be able to find that the monthly payment would be $12.83 under that structure. Obviously, that's with arithmetically increasing of 0. And we found that the I total, the amount we paid to the bank in interest, was about 10 grand. And then we were like, okay, if we structure that under the arithmetically increasing structure, will they be better for us, the consumer? And we're like, oh, well, our monthly payment is slightly lower than usual. It's about $150 less. And most importantly, we only end up paying $444 in interest, which is a lot, very different compared to that of just our level payments. And you might be thinking, well, why exactly is that? Keep in mind, up front, the majority of our payments will be allocated towards interest, because keep in mind, interest proportions of our payments are proportional to our outstanding balances. So if we are paying less payments up front, that means less of our payments are allocated towards interest across the entirety of our loan. Because when you look at your payments at the end of your loan, the majority of those payments are allocated towards principal, not interest, which under arithmetically increasing structures is where the larger payments are located towards the end of our loan life. Now, if you were to take this and turn it into an arithmetically decreasing annuity structure, then you actually should see that your interest is going to be at least potentially equal or potentially larger than that of a level fixed payment structure. And I leave that as an exercise for you. So, how does geometrically increasing loans look like in comparison? So again, if you want to sort of decide how big your monthly payment should be, obviously this is going to be equal to your M, where this is MK and this is your time value of K. These are going to be your exponentially increasing lines, right? So obviously we want that line to be as shallow as possible early on so that our loan payments are not allocating much towards interest, right? So this is obviously going to be a strategy. Choose G lower than your effective interest rate I, or generally speaking, choose a low G value, okay? So let's assume that our G is equal to 1.2%, and let's assume that's a monthly effective rate G. So each month our payments are going to increase by 1.2%. All right? So what is this going to be? Well, under the typical strategy, the present values must be equal to one another. So that means x must be equal to m divided by 1 over m divided by 1 plus g times a n under effective interest rate IG. Right? So that's going to be our structure. So if we solve this equation for m, then m is going to be equal to 1 plus g multiplied by, if we rewrite that annuity immediate, times that effective interest rate, or modified or adjusted effective interest rate, times our principal balance x, all over 1 minus nu to the power of n, and that's going to be our adjusted periodic discount factor g. So that's going to be our generalized structure for finding our monthly payment. Now let us jump into the numbers of our particular example. So again, I is going to be equal to our effective interest rate, unmodified. So that's going to be 1 plus 0.041 to the power of 1 over 12 minus 1, and that's going to be approximately equal to 0.00335. And our geometric rate g is chosen to be 0.012. Once you have these two particular objects, then you can find our adjusted effective interest rate IG, which again is going to be 1 plus I all over 1 plus g minus 1, which you should be able to find is approximately equal to negative 0.0085. You might be thinking, wait a minute, why is it negative? Don't worry, the math comes out in the end, so do not be scared. So obviously if IG is negative, then you should be seeing that nu g, which is 1 over 1 plus IG, is going to be positive. Right? That's going to be approximately 1.0086. Don't worry, the math still works out. All right, so once we look at that, what are we going to have? So our first monthly payment is going to be equal to M, which is going to be equal to 829.41. So that's going to be coming from that formula that we just stated just a moment ago. And that means our M2 is going to be equal to our M times 1 plus that G value. And that's going to be approximately equal to $839.36. It only increases by about $10, not too bad. And if we go all the way out to our last payment, which occurs at time t is equal to 72, that's going to be equal to M times 1 plus G to the power of 71. And that's going to be approximately equal to $1,934.58. Right? So that's how you can calculate our particular monthly payments. And most importantly, how do you calculate the amount that you paid total to the bank? Again, the starting formula is the same. It's just the sum from k is equal to 1 up to n of your mk, which from this particular structure, since m is constant, it's just going to be equal to the sum from k is equal to 1 to n of 1 plus g to the power of k minus 1. Right? Now, you should be able to notice that there is a discomfort between these particular things, and you can slightly rearrange it if you're interested in finding what this closed formula is equal to, because we can write that as m divided by 1 plus g times the sum from k is equal to 1 to n of 1 plus g to the power of k. And now we can use our typical summation relations to figure out what that is. And once you find a total, then you can find that I total will be equal to a total minus your principal. And then you can see if this is going to be lower or higher than your arithmetic interest accumulations. Take a guess of what you think it is, and then actually find the formula and then see what that value comes out to. But those are the principles associated to geometrically increasing annuity structures, and you can even start to think, what about geometrically decreasing annuity structures? What would be the difference in these formulaic structures? Hope you enjoyed this video, and I'll see you in the next one. Take care.